Okay, so today we'll talk about certificates. Which is um, backbone of digital trust. So certificates are everywhere. Certificates are indirectly part of your life, whether you are browsing internet, whether you are sending emails, doing connecting to VPN, you are texting on WhatsApp. So certificates are everywhere. You are indirectly using them, but what exactly happening in the background? We'll see that in today's session. So about me, so I'm Kalpesh. I'm working in miniOrange from last 10 years, and I'm working in cybersecurity domain for 12 years, which includes identity and access management, cloud security, blockchain. Um, okay, so to begin, what is digital certificate? So it is an electronic password which authenticate your devices, users, or servers. So, for example, let's say you want to provide access to application to certain employees. So you restrict access based on user certificates. Um, let's say you have company laptops and you want to provide access to only company laptops. That's a device certificate. And servers, what we mean by server is any website you are accessing is hosted on a server. So to check authenticity of the website, what it means is if you're browsing google.com, is it really google.com or is it a phishing page? So to check authenticity of that, we use certificates. So that in the this works with the use of cryptography and public key infrastructure, which we'll talk in detail in next slides. So what is purpose of purpose of digital certificates? So first is authentication. Authentication means, like we talked about, user authentication or device authentication. So certificates authenticated. Is it really you? Data integrity. So if we consider HTTP traffic, when traffic comes from a web application server to your machine, or a request goes from your machine to web application, is there any man in the middle who is changing the data or tampering the data? So that's data integrity. So data should be sent in the original form without tampering. And encryption. So not just stopping tampering, but data should not be visible because the data might contain your credit card information. Let's say you're doing shopping on e-commerce site. So whatever data is flowing, it contains your credentials, it contains your credit card information. So data encryption. So that we achieve with digital certificates. If we talk about type of certificates, there are couple of types I have listed. There are many. So SSL and TLS. So it's basically used to turn your HTTP site into HTTPS, adding encryption layer for your HTTP site. Client certificates, or we can also say device certificates, they are used to authenticate if it's really you. Code signing certificate. So certificates are used for when you package softwares. So the package softwares might be available to download for open source sites as well, not just on vendor sites. So when you download it, to check authenticity of the softwares, if they are from are they really from vendor, to check that authenticity, the signature is included with the the downloaded software. And you might have seen that vendor has also listed the same signature on their site. So what that is for is, whenever you download the packaged softwares from third-party sites. So you can, with that, you can check if that build was created by a vendor only, and now as it does not contain any tampered code or something malware, you can say. And the last one, email. So whenever you send emails, they are it contains confidential information. So we can't send email just like in a plain text. So everything is encrypted. So the certificates which are used to sign the to encrypt your emails, there are also digital certificates. Okay, so we'll talk about one of the certificate in detail. So let's say SSL and TLS. We'll go into detail for that. So understanding SSL and TLS certificate. So what they are used for is encrypting your traffic. So all the HTTP traffic, what is HTTP traffic is whenever you're browsing google.com or let's say aws.com, facebook.com, anything you're browsing is HTTP traffic. It includes two entities. One is your browser, which we will consider as a client, and second is the application server. So let's say your application code or HTML is hosted on the Google server, so we'll consider that as a server. So two entities are involved here, client and server, and communication happens between them. So to encrypt that communication, because the what HTTP traffic is, it is the packets, it is TCP packets, and it flows through the network only. So let's say you are sitting here, you and 100 others are connected to same Wi-Fi. So the traffic is going through same firewall or same router. So it's not hard that whatever you are browsing can't be seen by other members connected to same Wi-Fi. It's very easy. So if you keep it plain HTML, so anything can be sniffed. But so that's why there's a role of SSL and TLS. So it encrypts your traffic. So even if someone gets access to that, it can't be seen. So to understand that in detail, let's do that with a problem. There's a Chai Junction, let's say a local brand, which is right now has offline stores, and we have to take them off online. And online on an e-commerce store where they'll have online orders, logins, credit card transactions to purchase it online. So we have to secure all of that. So a first step. So Chai Junction goes barefoot. So what it means is for this case it is just HTTP. So as a first step, they have hosted a server. The server is live and users are using their online store, but it's just HTTP. So right now, what's the problem with this? So they are digital now, they are online now, but there is a man in the middle who can, like we talk about intranet, not just intranet, you can also, there can be a man in the middle who can just check your traffic, what users are browsing, what credentials are they sending, and all the confidential data. So that can be seen. So it's not solved yet. So they are online, but they're not secure. So one step forward, now the Chai Junction decides to put encryption in place. So they want that their data, their HTTP traffic should be encrypted. So they decides to put encryption in place. So now both the client and server have an encryption key. They are sending the traffic in an encrypted format, but there's a problem. How do they exchange a key? So when client sends, So when the client is sending the key to server first, the key exchange which is happening of the symmetric key, as man in the middle is able to see all the data, they are also able to see the encryption keys. So the problem with this approach is whenever you're sending the keys, it can be seen by the attacker. They can capture the keys, and once they get the keys, they can decrypt the encrypted traffic. So symmetric keys is not an option here. It can be decrypted easily. The attacker can get access to the key because you will have to transfer the key. You can't keep same key for all clients because that's again a problem. It can be easily decrypted. So for each connection, each HTTP connection, there is a unique key which is generated. And let's say client decides to generate a key. Client is a browser. For any HTTP traffic, client is a browser. So client decides to generate a key, and so there is a problem. How to send it to the server securely? Because the encryption will start after sending the key. So client and server should transfer keys without leaking. So how to achieve that? So for that, we have public key encryption at rescue. So what is public key encryption? So in public key encryption, you encrypt with one key that can only be decrypted with other key. So the key which is encrypting your data, you can't use that to decrypt. There's only one key which can decrypt, and that is also other than the key which is generating it. So I think this problem is not new. Mathematicians were working on solution for this from many years, and in 1970 that was finally solved, and they found a way. So in the background, it works with there are large prime numbers and RSA algorithm which is used to achieve that. So what happens is when you generate encrypted when you encrypt it with using large prime numbers with one key, that key is called as a public key, and there is a pair of key in here two keys. I'll just explain with this. So here you can see two keys. One is public key and one is private key. So for encryption we'll use public key, and for decryption a private key will be used. Each of them comes in a pair. So whenever you generate asymmetric keys, there are two pairs are generated always. One is public key, other is private key, and the asymmetric keys can be used. This is just an example of encryption, but they can be used for generating signatures as well. The case we saw for software builds or software packages where we use a signature. So that can be used. This combination can be used for signatures as well. So you can see the plain text was encrypted using public key into a ciphertext, and that can be decrypted using private key of the okay. So our challenge was, our problem statement was how to exchange keys without leaking. So in public key encryption, it is done with what we call handshake. So HTTP handshake is the method which is used to exchange the keys. So let's say client device sends hello message to the server, it just to establish connection. Then server sends back the server's public key, and once the client get public key from server, so client send back client's public key to the server. So now both the entities have the other entity's public key. So now client device can generate send the encrypted traffic using server's public key, and server has the encrypted the private key with it, so it can easily decrypt. And now only server can decrypt the traffic, and even if the attacker get access to the public key and also encrypted data, it does not matter. The attacker can't decrypt it, because the only key which was transferred in the handshake was public keys. Private key was with the generating entity only. So server generated its private key, so it was with the server only. It was never transferred on HTTP, or never transferred outside the server. And the client's key also, the private key generated by client also is with the client only. It was never transferred. So this is public key encryption and handshake. With this, we'll exchange the keys. So now you can see two keys here, one with the blue and one with the yellow. So yellow is client's public key, client's private key, and client sends the public key to the server. So you can see yellow public key there, and private key belongs to the server. The blue private key belongs to the server, and it transferred the blue public key to the client. So both have each other's public key and own private key, and they're now able to communicate securely with the HTTPS. Now this is done. So we have secured the traffic, we have encryption in place, but is there still an issue? Can there be the attacker which we are talking about, can the attacker still read the data? Okay, so let's look into that. So now, yeah, there is still possibility. So attacker can now put a proxy in middle, and the same thing which happened in the handshake with using public key encryption. So same thing attacker can replicate using proxy. Now here you can see the third key, which is red key, which belongs to attacker. In what we did earlier was exchanging the public key of the server and the client. Now what attacker is doing is, you can say the hello message which was sent from client to server, it was passed by attacker to the server. But when server is sending its public key, which is a blue key, attacker is changing it to its attacker's public key. So what client has now is the attacker's public key. And when client is sending its hello key to the server, attacker is changing that as well to the red key. And what server now has is attacker's public key. Okay, so what will happen now is whenever client will send encrypted message, it will be using attacker's public key now. So attacker can easily decrypt it, and attacker can just modify that message and forward it to the server using server's public key, because attacker already have server's public key, so it can send it to the server. And when server sends back the encrypted message, server has the attacker's public key, so that can also be read by attacker. So attacker is now acting as a man in the middle with a proxy, and all the communication is it can be still intercepted. So now what we do? What's the next step? So right now in the till now there was no verification of the key. It was a public key which was coming from the server. There was no verification that was it really sent by the server. Like let's say if we are browsing google.com, so the key which is coming, was it really sent by Google INC? and isn't it generated by a man in the middle? So there was no verification till now. So we'll put the certificate authorities in action. So what is certificate authority? So whenever you generate the certificates like public, private key pair we talked about, um, there are two ways to generate. One is self-signed certificates, like you generate them on your machine, use OpenSSL, you generate the certificates. So you can generate the same certificates, but they are not signed. So we call it self-signed. And the other way to generate certificate is from certificate authorities. So certificate authorities are like entities like GoDaddy or Cloudflare. So who provide you the certificates? And so when certificate authority generates the certificate, you have to send them a certificate signing request, which contains your public key. You still don't share your private key with them. So you just share your public key with certificate authorities. They sign it, they add their signature in the certificate and send it back. So now your certificate is not just a certificate, it is a certificate with signatures. The signature was added with certificate authorities private key. So there are limited certificate authorities. It's not easy for everyone to become certificate authorities. So now certificate authority has signed the certificate. Now you have a private key, your own private key, and the public key signed by certificates. So now whenever, so let's see now what happens. In the previous case, we were not verifying the generated certificate. Now see how it will work. So step 1, request from browser. Browser will send hello. So same handshake begins. So browser will send the hello to the server just to establish connection. Server will send the hello back and the server certificate. Now the certificates we have on the server are not self-signed certificates. They are the public key which belongs to server now is signed by CA authority. So it sends the server certificate and certificate chain, like who is your root CA, who is your intermediate CA. So that is sent back to the browser. Now the browser verification begins. Browser validates the received certificate with the first thing is chain of trust. The signature which we talked about, the signature which was stored inside the public certificate, now browser verifies region. So how do we verify the signature? So to verify signature, you need to have the public key of the certificate authority with you, and you try to generate the same, signature for same data. And if both signature matches, one which is coming in the response and one which you are generating, so that's how you verify if the signatures are valid. But how do you get the certificate authority's public key? So for that, all the machine, like if you are on Windows machine or Linux machine, or if you you are on Android or iOS, so all the devices have a root certificate authorities or a CA certs file installed on your OS. So what is CA cert file is it contains public keys from all trusted certificate authorities. So AWS, GoDaddy, everything which are in the trusted list. Everyone who can generate SSL certificates, all public keys are bundled in a CA cert file, and that is present on your OS. And when browser established the connection and browser tries to verify the signature, it sees that the public key which is coming is that the root CA for that, does that belong to your CA cert file? And if browser find that, it starts the process of signature verification. And if that happens, then only browser allows the connection to proceed. Not just that, there can be case that, let's say google.com does not belong to me, but Chai Junction belongs to me. So what I can do is I can generate the certificates for Chai Junction, get it signed by my CA, certificate authority, and I can use same certificates to do man in the middle on google.com. Would that work? No, because domain shake. So browser not just verifies the signature, it also verifies if the certificate which was sent, it has the domain name inside that. So it verifies the that domain as well, and validity of the certificate. Certificates are generally valid for 1 year only. So all the verification happens, and then only the next step is secure communication happens between the browser and the server. So that's it. So Chai Junction is live, secure, and traffic is all the users are now able to use that securely without worrying about getting intercepted by attackers. It is being used inside your company,
Right.
So you can. There is also one way that if you want to use self-signed certificate, the CA cert file I mentioned, which has GoDaddy, AWS certificates only, in that you can add your own company's certificate only as a trusted certificate, so that for at least for your intranet, you don't have to purchase certificate. It can run with self-signed certificate, and it will become trusted as you are adding the root CA into the CA cert file.
My second question is in continuation with the first question. What is the cost for taking certification if it is signed or from trusted authority? If I am taking the certificate, how much it cost? And
Okay.
who is the root authority for India?
Okay, so for India there are multiple. So it's not specific to region. So GoDaddy is very popular. AWS is very popular. There are multiple. Sectigo. So hundreds of root CA certificate authorities are there, and cost is different for each. But I'll say that if you want to do it for one domain, which is google.com, so it will cost around, let's say, 10,000 per year. But if you want to do for wildcard is star.google.com. Any subdomain, even if you access any subdomain, it should have SSL certificate. So that costs around 10 times higher.
10 times?
Yeah, but there is one way, Let's Encrypt. Have you heard of Let's Encrypt? So what you can do with Let's Encrypt is get all the benefits which other CAs are providing, but it will be valid only for 3 months.
Achha.
And after 3 months, there is a tool which auto-renew it. So CertBot is a tool with which you can auto-renew. So same benefits you can get. Only thing is sorry?
It is free there.
It is free. So Let's Encrypt you can try. Same like we did with OpenSSL, you can generate Let's Encrypt certificate with the commands.
Achha.
And it gets auto-renewed after 3 months. So you don't have to pay to the certificate authorities.
Thank you, sir.
Okay. Any other questions? Yeah. Can you please?
I wanted to ask that are there any software or AI based software which are extended to our Google servers which can identify for the users that the web page which he or she has accessed is a hacker based web page or a legit Google. The Google domain is all the letters are small, but the hacker can use one letter big and it can access. It gives access.
Okay, so what you are asking is, are there AI-based softwares which can point out if you are on a phishing domain or not? Right. So for that, companies are working on creating a browser extension, a secure browser extension. So what that browser extension does, it has domain list of all the trusted domain names. like google.com is in its list, and they have AI based pattern matching. If the domain name which is coming is very similar to google.com, like google.com with triple-o.com, then they are pointing out that they are showing a red page in the browser itself that, are you sure you are trying to access google.com with triple-o and not google.com? So there are browser extensions, and in the backend they are using AI. Splunk. Not on Splunk, because Splunk is an analytics tool, right? So I'm not sure what use case you're trying to talk about, but whatever phishing happens is on the browser. You type it on the browser or clients, like Firefox, Chrome, or mobile Safari. So there are your clients. So in Splunk, not sure what would be the use case. Sorry?
Is this type of extension available in Splunk type applications?
No, I think.
Companies can use.
Because Splunk is not a client. Splunk is application server itself, right?
Yes.
So this type of application's need will be for client. Client is your browser. It will work with client application.
But are there any companies which are trying to build like this type of application?
There are many. Yeah.
Okay.
So you can find that in Chrome extension.
Thank you.
So hello.
Yeah.
So my question is, so there are so many open source tools. So one of them is EvilJinx. So it basically do the man in the middle attack, and it setups everything on its own, like exchange of certificates, setting up the DNS records, all of the things, and it is open source. So anyone from you can set up your own man in the middle attack. So the thing is, what we can do to avoid such kind of open source tools, so companies like will not get hacked easily, because it is setting everything on its own and it's ready to use. So what we can do exactly?
What tool did you mention?
EvilJinx.
Okay.
It is open source tools. It do everything all on its own. Setting exchange of all the certificates, DNS records, and all the things actually.
So didn't get that properly. So you mentioned that there is a tool which does automate everything.
Yeah. So what we can do to avoid such things?
Okay. I think if the tools are generating certificates and or doing operations around certificates, that can't be avoided. But to avoid getting to avoid man in the middle, there are things which people are working on. Is one which we just talked about, browser extension, which tells you if you are on the phishing domain, then the verifying certificate authorities. Even the tool which you mentioned can't generate the certificates same like certificate authorities.
It's for actually the fake domains, but it's generating the certificates. It generates that SSL and TLS, but it will be the double or triple google.com. Like that.
There will be self-signed, right?
Yeah.
Okay, so if any tool is generating self-signed, you can't avoid that because OpenSSL is also there.
Yeah, but the data is transferred with the EvilJinx, and then it further transferred to real google.com. So in the middle, it will just you can say monitor or extract the credentials and then pass it to the real authentication backend of the Google.
Okay.
So it is just extracting, let's say, the credential in the middle and passing it to the real Google authentication backend with all the cookies and everything.
Understand. So probably we can discuss offline. I'll probably take a look at that tool and check so that I can get understanding what exactly is happening.
Yeah.
So that I'll be able to answer.
Yeah. Thank you so much.